Hello. So in this video, I want to show you how we can analyze sediment or soil samples to construct their particle size distribution curve, which will allow us to characterize these sediments statistically. For example, describe the median grain diameter, D50, or the mean grain diameter, look at their salting, skewness, and kurtosis. Now, particle size distribution is really important because if we want to construct a building or a structure above soil or sediment, then the strength of that soil, its varying capacity, is really a function of the sediment size and its sorting or packing. The same applies if we want to describe how water flows through an aquifer, for example, because again, the speed at which water could flow through this porous medium depends on how tightly packed these particles are, and that's really a function of their composition. If we also want to describe the sediment movement, for example, how waves move sands on beaches or rivers move sediments, gravels on their bed, then again, the mode of transport and the rate of transport are also a function of that sediment size or soil size. And so the particle size distribution really gives us a very powerful statistical tool that will allow us to use these conventional empirical equations to describe water flow through porous medium, sediment transport rates, or even soil varying capacity. So the sediment sample I have here today is from a coastal setting. So this is sediment collected from Eastern Beach in the UK, in the southeast coast of England, along the Solent. And because it comes from a salty environment, then the first step is actually to pre-process the sample. That simply means we need to wash it with clean or distilled water to remove all the salts, and then drying it in an oven overnight. So usually we dry it at 100 degrees Celsius for about 24 hours. Now, if we think there is some mud or silt in this particle that we're interested in preserving, then we need to collect the water that goes through a very fine sieve while we wash these particles, what we call wet sieving, and then allow that water to settle in a column and collect any residue and analyze that in the coarser fraction, the sands and gravels. And sands and gravels are really defined based on their particle size. So sand pertains to any particles that are bigger than 63 micrometers in diameter and up to 2 millimeters, beyond which we classify particles as gravel. So anything between 2 millimeters and upwards, we classify that as gravel. And this distinction between particle sizes is known as the Wentworth-Miller scale. And I've got a copy here, which you can download from Wikipedia, pretty good graph. And it distinguishes different classes of sediments. So we've got clays and silts, the very fine particles, and then we've got sands, pebbles, and then cobbles or boulders. And this distinction here is at the 63 micron mesh. Now, the Wentworth-Miller scale is really based on what we call phi units, and phi units are used largely by geologists, and that's a function where it tries to distinguish these classes in whole numbers, and therefore it's defined as log to the base 2 of the diameter of the sediment in millimeters. Now I want to do dry sieving, and dry sieving is an easy technique that will allow us to divide this sediment sample into different size classes. And we do this by constructing a stack of meshes of increasing aperture sizes. So this is a standard sieve, and you can see it's constructed out of a mesh with a defined spacing between them. And they go from larger mesh openings at the top to smaller mesh openings at the bottom. Now we usually want to do this consistently, so we either sieve our sediment or our soil in classes that jump by a half phi scale or by a quarter phi scale. So what I'm going to do today is really sieve at a half phi grading, and so I will need sieve sizes that are 63 microns, so that's our lower limit for sand, and then the next one up will be 90 microns, which I've got here, and then I've got 125, 180, 250, 500, 7, 10, 1, 1.4, and 2 millimeters at the top. And I think I skipped 0.355, 355, which sits in here. Okay, so that's our sieve size. So we've got pretty much everything we need to do. We've got our dry sediment or soil sample, we've got our stack of sieves, and we've got our mechanical sieve shaker. So that will make life a lot easier. We also need a scale that will allow us to measure the mass of sediment retained in every mesh here, so at every class size. And because we want to do replicates, we want to subsample our sediment, and so I've got here a riffle box. So to subsample our sediment, we can do two things. We can either use a riffle box, which is essentially this construction here that allows us to randomly select sediment and split our sample into two boxes. So we can analyze one, then analyze the other one, and therefore have a replicate of our sample to be more robust statistically. If you don't have a riffle box like this, you can do quarterly. That simply means gently lowering your sediment into a mound. So I'm doing this over a paper here, white paper, so I don't use much of the material. And I'm using the brush to get the sediment out. And now I want to make it into a cone, effectively. And then you can split it into half. And then across to give us our 4 sub-samples. And you can analyze each of these separately. However, I'm going to use the riffle box. Now just notice that our particles include relatively large pieces of gravel, which are not going to go through this riffle box, so I'm going to be using a slightly larger one. It's really important to check that it is clean and empty before we start. Okay? Now what I want to do is, hopefully without losing my sediment, is pour this across. And we can see some particles didn't go through, but I can just about guess that this would have gone here, this here, this there, and this there. And now I have 2 samples that have been randomly selected, so I can do my analysis. Okay. So the next thing is actually to do the sieving. Now, if you read through the British standards, we are required to sieve a given amount of sediment for our analysis for sands. So if it's fine to medium sands, we want around 100 to 200 grams. If it's relatively coarse sand, you perhaps want to sieve at least 500 grams. And I reckon we have about 500 grams here. So this is really a bimodal sediment. I can see that very clearly because there is a lot of sand in here, but there's also a considerable fraction of gravel as well. So before we start sieving our first sample, we really need to measure the weight of sediment here at the beginning, and at the end we're going to compare that with the cumulative sum of the sediment masses retained in every class and assess if we've lost or maybe gained any in the process. So it gives us some quantitative measurement of any error in sieving. Okay. So I've got my extra sieves here, 2.8, 4, 5.6 and 8, and we're ready to go. So I've got the rest of my stack here now. That goes all the way from 63 micron to 8 millimeters, jumping at half-5 scale. Now you can see that this is much taller than the height of my sieve shaker, so I'm going to have to split this in 2 goes. I'll have to do this twice. So I'm going to take the top part first, analyze that, and anything that is retained at the bottom is then brought into the second set down. Okay. Now obviously I need to make sure that I've got a tray at the bottom to retain any sediment that is smaller than 63 microns. And I'm going to pour my sediment sample at the very top and use the brush to make sure that I get all the fine stuff that might be stuck there because of electrostatic forces. Okay, now that's ready. To go on the sieve shaker, I need to put a cover plate at the top, so I need to get that. And that sits here. I'm going to put the rubber to minimize the noise. And then I'm going to clamp this so that it's secure and tight. Okay. And now it's programmed to run for 10 minutes at a relatively medium power range. And I will start it. It's going to be very noisy. Okay. So now we've sieved this for 10 minutes in the upper part. Okay. And you can see here that in every side some sediment has been retained. And again the next one up, or the next one down I should say, and so on. And we also have some that's been retained at the very bottom. And surprise, most of the sand has. So that now has to go into the next part of the sieve chain, and then again that will have to go in for 10 minutes. So what I'm going to do now is weigh how much sediment has been retained in every sieve class. So to do this, again, I need my trusted balance. I need some paper weights or any container that is light enough. I need my brush and obviously my notepad. Okay, so to make things easier, I've got my paper, which I've creased in the middle to make pouring easier. I'm going to start by taking the very top sieve. So this is 8 millimeters in aperture size. I'm going to tip my sediment gently along it because I don't want things to fly out. Nearly lost a particle here. And then with a brush, these particles are large enough, then just sieve everything through. Okay. And I need to weigh this material, the largest fraction. So I've got a paper boat here on my scale. I'm going to zero that. And then I'm going to transfer this through and weigh that material. So 159.3 grams. Our sediment has been sieved now and divided into half-phi scales, going all the way from 8 millimeters in here all the way to sand size just around there, and then finer material at the end. Now, so here we have it. We just finished the first replicate. I will do the same again for the next replicate. Usually you do about 3 replicates or 4 replicates per site, so you could quantify the errors. Another thing I have to do really is digitize this and use a software to plot the data, or do it manually if you want to. I'll show you. Okay, so now that I've got all my within masses, I'm ready to analyze the data. I'm using this piece of software called GradiStat, which is based on a paper by Philosophy Pi, and you can download the software online from their website. Here I'm just inputting the sample identity, the date, and the initial sample weight. This is my first replicate. I could obviously do this for multiple replicates. And using quarter-phi intervals, I've inputted the mass retained in grams for every class aperture size. So we started with 8 millimeters or 8,000 microns all the way down to 6,000. The initial weight here is important because we can sum of these retained masses and compare these to see if there is any loss of sediment during the process. So it quantifies our error. If I just calculate statistics, it says the statistics have been computed, and we seem to have gained less than 0.1% of our initial sample weight, so this is acceptable. It is also clever enough to tell us that this sample is not unimodal, and therefore we have to be careful how we interpret sorting, skewness, and kurtosis. Anyway, it's giving us a really good description of the sediments. So it's telling us that this is a bimodal, very poorly sorted sandy medium gravel. So textural group would be sandy gravel. And it's also given us the percentile. So the 10th percentile, D10, It basically means 10% of the sediment has a grain diameter equal or less than 273 micrometers or minus 3.35. The D50 or the median grain diameter, which is very commonly used, again, that means half of the sediment sizes are equal to or less than 6.3 millimeters, and the other half is larger than 6.3 millimeters. Then D90, which is the upper 10th percentile, or the 90th percentile, tells us that 90% of the sediment has a diameter equal to or less than 10 millimeters point 2. It's also telling us that about 73% of the sediment is gravel and just over a quarter is sand. Therefore, it's a sandy gravel. It's predominantly gravel by now. And again, we've got the mean, sorting, skewness, and kurtosis, and it produces a graph, a bar chart, if you like, of grain size distribution. And you can see very clearly that this is bimodal. We've got a peak on the sand fraction and a peak. And if we want to plot the cumulative particle size distribution and the cumulative distribution, then again we can do this quite easily. And there you have it.